We now want to start the verification of the Eilenberg-Steenrod axioms for singular homology, and actually the first axiom we will take care of is the long exact sequence axiom. And this video now is meant as a preparatory class for proving this axiom for singular homology, because it turns out that this is actually only a consequence of algebra. So we will now prove a purely algebraic lemma, from which then the long exact sequence will just follow immediately, or more or less immediately. And this lemma actually has gained quite some notoriety. It has also a unique name. Namely, it's called the snake lemma. Okay, so what does it say? It's a lemma about a diagram in the category of R modules. So let's draw this diagram right away. We start with one R module A, got another one B here, yet another one here called C. And we've got another row of such modules, call them A prime, B prime, and C prime. And now we also have arrows in the vertical direction pointing from A to A prime, B to B prime, C to C prime. And finally, we extend this diagram by a 0 up here and a 0 down here. And in order to talk about all those arrows later on, let's give them names. So this vertical one is called F, this one is G, that's H. The first horizontal one is I, the second one is J, and the lower ones consequently get a prime, I prime and J prime. Okay, so this is sort of the input data of the lemma. So let this be a diagram in the category R mod of R modules, where as usual R denotes a commutative ring. And we require that in this diagram, the rows, so the horizontal parts of the diagram, are actually exact. Yeah? So remember, that means the kernel of one arrow is the image of the preceding arrow. And this is what we require for all objects in these horizontal sequences. So let this be a diagram in R mod with exact rows. Okay, so those are the prerequisites of the lemma, and then the statement is that we obtain from this an exact sequence. Then we obtain an exact sequence of R modules, which looks as follows. So it starts at the kernel of F, so here at this submodule of A, at the kernel of F. From there we get a map into the kernel of G, and then further on to the kernel of H. And then we've got a mysterious homomorphism, which we will have to explain in the course of proving this lemma, called delta, also called the connecting homomorphism. Now from the kernel of H to the co-kernel of F. And from there, the exact sequence keeps on going to the co-kernel of G, and finally to the co-kernel of H. Yeah? So the statement of the lemma is that this sequence of R modules is exact everywhere. And the snake lemma has a second part. Namely, if we in addition require that there's another 0 here, such that this row is still, exact, and yet another 0 here, such that the lower row is still exact, then we also gain something more. Namely, then we can extend this exact sequence by a 0 in the beginning and by a 0 in the end. So we additionally obtain that this morphism here is injective and this morphism here is surjective. Okay, so far so good. That's the statement of the snake lemma. But of course at this point one might wonder, why is it called the snake lemma? So we should see a snake somewhere here. And actually the snake can be pictured. So how does that work? Let me copy the diagram we have up here. Whoops. I have to take the copying tool, this one. Gotta be careful not to grab anything else, but this looks fine. Copy, and then I'll draw it again down here. So maybe here, paste. Okay, so I can now already explain some of the morphisms appearing in this exact sequence, namely the first two and the last two. And so where do they come from? Well, I can just extend this diagram, namely the kernel of f, that's a submodule of A here, of course, so I can include this here. This is just the inclusion of the submodule kernel f. And in the same fashion, we've got the kernel of G here, and we've got the kernel of C here, the kernel of, of H here. And now this morphism from kernel F to kernel G, this is simply the restriction of I here. And at the same time here, the morphism from kernel G to kernel H, that's the restriction of J. So in other words, there's already a little statement that happened here. Yeah, if I'm claiming here that if I take an element in A which lies in the kernel of F, then under I it is mapped to the kernel of G. Yeah? So maybe that's a condition we should already verify at this point. So let's see. So say we've got an element in the kernel of F, so it lies in A and is mapped by F to 0. Then since I prime is a homomorphism, it of course maps 0 to 0. So if I follow this composition with this element I chose here in A, then I get 0. But by the commutativity of this square, this means if I follow this composition for this element, I also get 0. But that of course means if I go over here and afterwards I apply G, I get 0, meaning the image of the element under I lies in the kernel of G. So it's got to live here, and it's true that the kernel of F maps into the kernel of G. So that's the argument here, and precisely the same argument also works for this square here. So also the kernel of G maps into the kernel of H just because this square here commutes. Okay, so this explains the first two morphisms here of our exact sequence, this one and this one. And now we can extend this diagram even further. Namely, we can draw an arrow here to the co-kernel of F.
So just in case somebody wondered and hasn't heard the terminology co-kernel yet, it's just A prime in that case divided by the image of F.
Yes, that's a good point. So co-kernel is target modulo image. In this case, it's A prime modulo the image of F. And the notion of co-kernel is dual to the notion of kernel, yeah, in the sense that, well, a morphism F is injective if and only if the kernel is trivial, and a morphism is surjective if and only if the co-kernel is trivial. Okay, so that's why this is just a projection map, yeah, a projection into a quotient of A prime. And likewise, we here got the co-kernel of G, and here we've got the co-kernel of H. And I claim, or I'd better say the lemma claims, that the morphism I prime here from A prime to B prime descends to a homomorphism from the co-kernel of F to the co-kernel of G. And what's the condition you have to verify that such a morphism descends to a morphism of quotients? Well, the submodule that you factor out, which is the image of F here, needs to be mapped by I prime to the submodule that you factor out here, which is the image of G. So why is that true? Well, if I take an element in the image of F here, that means, well, I've got a lift here, got an element here which maps to that element, but then I can map that element via I to B, and if I map that element in B down by G to B prime, then by commutativity of the square, well, I end up at the element that I get if I, from the very start, had mapped that element in A prime by I prime to B prime. Okay, so that was maybe hard to formulate, but it precisely meant that if I start with an element in the image of E, in the image of F, I end up at an element in the image of G. And that means I've got an induced morphism down here. And again, precisely the same argument repeating for this part of the diagram yields a morphism from the co-kernel of G. Oh, this is the co-kernel of H, excuse me. To the co-kernel of H. Let's leave a bit of space. Okay, so far so good. So this explains the last two morphisms of our exact sequence, this one and this one. And now what I had really promised was to explain why it's the snake lemma. Well, we still need to talk about the homomorphism delta appearing here from the kernel of H to the co-kernel of F. And if one even wants to draw this homomorphism in this complicated diagram, well, then there's only one way one can do it. Well, one has to start here at the kernel of H, and one has to end up here at the co-kernel of F. So the way one usually draws it is like this. You wind around here in the diagram, and then I go along here, go along here, wind around this part of the diagram, and end up at the co-kernel of F. And this is what's called the connecting homomorphism delta. And I think now there are no questions left why the snake lemma is called the snake lemma.
So in the usual statement of the snake lemma, there is sometimes an additional fact, namely that this construction is natural. Could you go up to this statement again?
I probably forgot to mention it.
So that you obtain a natural exact sequence.
Thank you for saying this, because I definitely want to make this part of the statement. Get it right. Then we obtain a natural exact sequence in this way. Yes.
It's not so clear what natural actually means, right? So natural means that if you have, you should think of this diagram above with the A, B, C, A prime, B prime, C prime, maybe as a plane in our three-dimensional space. And then we have another plane with such a diagram parallel to that. And then we have connecting maps so that we get a commutative cube.
Yes.
And such a commutative cube then gives rise to a commutative ladder of exact sequences.
Exactly, yeah. So if we have two copies of this diagram which are connected by morphisms, then the corresponding long exact sequences are also connected, giving sort of a horizontal commutative ladder. That's how one could think about it. This is what naturality means in this case. And yeah, maybe let's also make a statement here in between the sequence and the diagram. So then we obtain a natural exact sequence which can be pictured. By the diagram. That follows here. Okay. All right, so I think the statement should now be clear, including the naturality statement. So now we got to prove this lemma. So let's enter the proof, and let's first of all collect what we got to do. So first of all, we just talked about the first two morphisms appearing in the exact sequence and the last two morphisms appearing in the exact sequence. So there's one very important morphism we still have to construct, and that's the connecting homomorphism delta. So yeah, just let me write task list here. And then the first task is going to be construct the homomorphism delta. Okay, then the second part of the statements of this lemma is the exactness at all those various places. So show exactness, that's the second task. And finally, there is the naturality statement. So show naturality. This is what we have to do. And in order not to overload this video, I decided that we will do the first part in detail because this is sort of the most important thing, this connecting homomorphism. We should really understand how it arises and why it is a homomorphism that's well defined. And so this is what we'll do. We'll do 1. And the exactness, this we will only exemplify at one particular part of the sequence. So exemplify 2 at, say, the kernel of G. Because in any case, all the arguments that are used for this part of the diagram more or less repeat for the rest of this exact sequence. So it's once you have grasped the idea how to do this, you will have little trouble in doing it at the other parts of the sequence. So let's just do this at one spot. And finally, we'll skip part 3. Yeah, we'll not do naturality in this video. Exemplify 2 at kernel 3, kernel G, and skip part 3. Where skipping, of course, means that you should do it at home, right? This is how we usually proceed here. Okay, so how do we
prove so much that we build enough trust?
Yeah,
the audience believe
this is how I should
correct.
put it. Yeah. Exactly. Yeah. Okay. So part 1. How do we construct this homomorphism delta? So before I give the formal proof or write down the exact construction, I should maybe just illustrate it how it works. So I'll pull up the diagram again, and let's see how we get this homomorphism delta. So it's got to start at an element here in the kernel of H, yeah, and we got to come up with an element in the co-kernel of F. So how do we do it? Well, we fight ourselves through the jungle here, yeah? So we really have to go through the diagram and see how we finally arrive here. So let's do this. Let's start with an element C from C, which lies in the kernel of H. Okay, so we've got an element C here, and the map J is surjective by the 0 that's written here and the exactness of the sequence. Yeah? So this morphism G is therefore surjective, and we can find a pre-image of this element C under J in B. Next thing we do is we take this element, this pre-image which we just chose, and map it via G down to B prime. Okay, then we're here, we've got an element in B prime. What can we do with it? Well, only one thing, we can map it via J prime to C prime. So what happens then is, by the commutativity of this square, we arrive at the same element as if we had mapped the element here, the chosen pre-image, along this composition down here. But this was chosen as a pre-image of the original element, which was chosen from the kernel of H. In other words, it's mapped to 0 here. So therefore, the image of the pre-image we chose here is mapped by J prime to 0 in C prime. That means it lies in the kernel of J prime. Now by the exactness of this lower sequence, this one here, the element we have here in the kernel of J prime lies in the image of I prime. The kernel of J prime is equal to the image of I prime. This means we can find a pre-image under I prime of this element. So then finally we are in A prime, we've got an element here, and this one we push down to the quotient here, co-kernel F, and this is our definition of delta of the element we started with. Okay? So that was kind of a lot to grasp, so let's write it down again. So this program carried out now looks as follows. So we started with an element C in the kernel of H. And now the argument was that since J is injective by the exactness of the upper sequence, since G is surjective, we find the pre-image, we find B in B with a property that it maps to C under J. So J of B equals C. Now the next argument was we have J prime of G of B. So if we map this G of B by J prime over to the right, then by the commutativity of the right-hand square, this is the same as H after J of B. And now j of b, that was of course just c. And c was chosen from the kernel of h, and therefore this is 0. So what does this mean now? This means the element a, b, c, d, e, f, g of b lies in the kernel of j prime. And the kernel of j prime, by the exactness of the lower sequence, is the image of I prime. So this in turn means, thus there is some element a prime in a prime, the lower left corner of the diagram, with the property that if I apply I prime to it, I end up at g of b. And this element a prime, which I now have found, this is the one I used to define my homomorphism delta. We just set delta of the c we started with is equal to a prime, and I just write plus image f. Yeah, so this is my notation for an element in this quotient. Yeah, I just write this coset like this, a prime plus the image of f. Okay, so of course, whosoever has some experience in mathematics will realize that there's something to be done here. We made a choice. Yeah, so when we define something using a choice, we have to check well-definedness. Yeah, so why did it not matter which choices we made? So let me just put it down. Check well-defined. So let's first of all be clear about what we actually chose here. What was the arbitrary part? Let's get back to the diagram.
There was only one choice, really, right?
That's right, there was only one choice. Namely, when we chose a pre-image of the element from the kernel of H we started with under J. There we made a choice. Yeah, this was just a surjective map, which is not necessarily injective. So there were various possibilities here. But as Roman pointed out, there was another pre-image we sort of chose, but that was not a choice because this I prime morphism, which we used here to pull back an element from B prime to A prime, that is injective by the 0 that's here. Yeah? So therefore, this has only one pre-image and there was no choice left. So the only thing we have to take care of is what would have happened if we had chosen a different pre-image here.
Maybe before you go down to the formal proof, one can think maybe for a second what the diagram proof is, right? So, I mean, this whole technique of arguing with the diagram without actually writing down elements is called diagram chase.
I mean, and for obvious reasons.
Yeah. For obvious reasons, need some practice to get used to it, but sometimes easier to understand, and it's very suited for videos. So you told us the construction of delta by a diagram chase, and maybe we can see at least the idea for the for being well defined looking at the diagram. So if you choose, so you go from the kernel of H and you go down to C, now you choose a pre-image. So suppose you choose a different pre-image, then what would it look like? It would look like the other pre-image plus an element coming from A.
That's right, because if I take the difference of those two elements, the old one and the new one I chose, and I map this difference by J to C, I get 0, right? Because both were pre-images of the same element. And then that means this difference lies in the kernel of J, and by exactness in the image of A. So I find an element here which maps to this difference here.
Right, so you have these two elements in B, where the other one is just the difference is plus an element in A. And if you map this down further to B prime and take the pre-image, the now unique pre-image in A prime, how do these two elements in A prime that you get for the two different choices differ? Well, they differ just by an element that's now actually coming from A.
Yes, they differ by f of A, where A was the pre-image of this difference.
Exactly.
Yes.
And now if you go further down to the co-kernel, this difference summoned just vanishes in the co-kernel.
Yeah, so if it comes from here, it lies in the image, and the image is the 0 element in this co-kernel. That's exactly the proof, but yeah, I still hope it helps if we write it down so that one has a record of it. So let's just put down here what we just said. Oops. So let's check the well-definedness. Let's carry out the program we just discussed. So just saying, had we chosen a different element, so had we chosen B plus IA instead of B as pre-image, of C under J. Yeah, so remember we just discussed why we can assume this different element has this form. It's B plus IA. Then, well, what happens to this element if we follow the procedure of constructing the homomorphism delta? Well, we apply G to this element, so G of B plus IA. This would then be, let's put it up, by the homomorphism property G of B plus G of IA. And now I copy G of B, and here I use commutativity of the square, of the left-hand square actually. G of I of A is the same as I prime of F of A. So this is the calculation, and therefore the unique pre-image under I prime of this G of B plus IA, yeah, is just A prime plus F of A. Yeah, because if I apply I prime to this element here, then I end up at the element I wanted, at G of B plus I prime of F of A. So there's only one such choice because I prime is injective, so this one is the unique pre-image. And this one, A prime plus F of A, this one equals A prime in the co-kernel of F. Yeah, because they just differ by an element in the image of F. Okay, so far so good. So let's collect what we got. First of all, we have defined this homomorphism as a map from the kernel of F, from the kernel of H to the co-kernel of F. And we also checked that this really is well defined, yeah, that the choices didn't matter. But something one can easily overlook is at no point is it clear that this map of sets that we just defined is actually a homomorphism. Yeah? It was defined by a construction, a choice, and so on, so there's no way we can easily know from the very start that this is a homomorphism. So that's something that needs proof as well. So this is the next thing we have to consider. We check it's a homomorphism. Okay, so what is it that we have to check? Well, we have to check that delta of C1 plus delta of C2 is the same as delta of, in parentheses, C1 plus C2. Yeah? So let's give all these elements names. So let delta of C1 be now A1 prime plus image F. So I'm using the construction I just explained and put down here. Yeah? So I take a pre-image up there, and I map it down by G, and then I take a pre-image and get an element, in this case A1 prime, and consider its coset in the co-kernel. So this one is the first one. Then secondly, delta of C2 is supposed to be A2 prime plus the image of F. And finally, I consider the element delta of C1 plus C2, and this likewise is constructed the way before, and this element we come up with in A prime, or in the co-kernel actually, of F. This one I denote by A3 prime plus the image of F. Okay. So now the homomorphism property of course means that this one, delta of C1 plus C2, is the sum of the other two. So let's write down what this means. Got to show if I take a1 prime plus a2 prime, and I subtract now a3 prime, then this is supposed to be 0 in the co-kernel, which means it's in the image of f. Yeah? So if this equality holds, then I get the homomorphism property in the end. So this is what we have to show. So let's see why that is true. Indeed. And now the proof works as usual in this diagram chasing things. You take your element you have to verify a property about, and then you always do the only thing you can ever do with it. Usually it's just one arrow you can apply to it, and usually then you will end up where you want to go. So what can I do with an element of a prime? Well, basically the only thing I can do is I can apply I prime. So let's do that. I prime of a1 prime plus a2 prime minus a3 prime. This is now by, well, the construction using the notation during the construction, g of b1 plus b2 minus b3. Yeah, the index denotes from about what element I'm talking about here. And now I'm in an element of, I have got an element of b prime here. So there's only one thing again, what I can, I've got an element of b prime here, but this element inside the parenthesis is an element of b, and there's only one thing I can do with b. Elements from b, I can apply j to it. So this is the next thing I consider, j of b1 plus b2 minus b3. And this now gives me the elements I started with. So that's c1 plus c2, and the b3 is the one which corresponds to c1 plus c2. So it actually turns out that this is equal to 0. No? And now again, there's only one thing I can say now. Well, this just means that this element lies in the kernel of J. So therefore, okay, so maybe I shorten this up. Therefore, this element lies in the kernel of J, which by exactness of the upper sequence is equal to the image of I, and therefore I find a pre-image under I. So therefore, there is A in A, such that I maps this element to this sum. So such that I of A equals b1 plus b2 minus b3. Okay, right. So this element A is the new thing I've constructed now. What can I do with an element A, from capital A? The only thing I can do is apply F to it. So let's do that. This gives, well, an element f of A, which now lies in A prime. The only thing I can do with an element of A prime, really, is applying I prime to it. So I apply I prime to it. And then the only thing I can do next is use commutativity in this square. So I prime after F is the same as G after I of A. Okay. But now I of A, I just plug in from above, is the same as G of B1 plus B2 minus B3. Okay. And G of B1 plus B2 minus B3, this I take from up here. Whoops, does one see the pointer? Yeah. This is the same as I prime of A1 prime plus A2 prime minus A3 prime. So this is then the same as I prime of A1 prime plus A2 prime minus A3 prime. And now the final step. We've got an equality here of elements mapped under I prime. I prime of f of A is equal to I prime of A1 prime plus A2 prime minus A3 prime. But I prime is injective. And therefore, if these two images here are equal, yeah, then these corresponding pre-images must be equal too. So since I prime is injective, it follows that what's in the argument here must be equal. That f of a equals a1 prime plus a2 prime minus a3 prime. And in case you forgot, this is exactly the equation we had wanted to show. Yeah? This a1 prime plus a2 prime minus a3 prime lies in the image of image of f. And it does because we just constructed the pre-image. Okay, so this was the homomorphism property, and we now have seen that we have now constructed the connecting homomorphism, shown that it's well defined, and shown that it's a homomorphism. So the first part of the proof is now completed. The next thing I had in my task list was to show exactness. So I had said I wanted to do this only at kernel of G, and well, now I'm sort of got tired of writing down all these arguments, so this I will really do just as a diagram chase. So this is yet another diagram chase. Which I now perform here live at the diagram. So let's see. Where is it? No.
It's a lot of text if you do a diagram
Yeah,
chase
exactly.
written down.
It does produce text, that's true. Okay, so I want to show exactness at kernel G. So that means I have to show two inclusions. I have to show that the kernel of this homomorphism is contained in the image of this homomorphism and vice versa. And one of the two should be easier than the other. Well, if I have an element in the image of this morphism, yeah, and I map it forward along this morphism, I mean, remember these arrows are just restrictions. That means I map it along two consecutive arrows in an exact sequence, and this gives 0, yeah? Because the image of this map is not only contained, it's actually equal to the kernel of this map. So in particular, it's 0 if I map it along two arrows. And this means precisely, well, the image of this homomorphism here is contained in the kernel of this homomorphism. Well, this was easy. The other direction is probably a little chase. So let's see. If I've got an element in the kernel of this homomorphism here, that means, well, it's just restriction. So this is an element down here in B, which is mapped by J to 0. So it lies in the kernel of J, which by exactness is equal to the image of I. So it's got a pre-image here. Actually, this is what we want. We want a pre-image, right? We want to show it's in the image of this map. The only thing that remains to verify now is that this pre-image here lies in the kernel of F. Yeah? So if I map this element down with F to here, yeah, then I don't know yet that it's 0. But if I afterwards compose it with I prime, then this is the same as if I had mapped it along this composition by commutativity. And now remember that we had started with an element in the kernel of G. So this composition is 0 then, because applying G to it gives 0. So that means the pre-image I have here is mapped to 0 here. But now remember that I prime is an injective map, yeah, because of exactness here. And injective maps have the property that they only map a 0 element to 0. So since it's 0 along this composition, it's actually already 0 here, which means this pre-image we got here does actually lie in the kernel of F, and that proves the image, the kernel of this homomorphism is contained in the image of this homomorphism. And this is the other inclusion. Okay, so this was part 2 of the proof. Third part of the proof is the easiest. I said I'd skip naturality, so you're invited to try this at home. And this is all.